Hello again and welcome to another GCSE Computer Science Theory lesson. This video is going to be on Unit 3, Images. So let's get started with the term pixels. So pixels are the smallest part of an image. Every image on your computer is made out of pixels. With an image with an old-fashioned graphic like this from the old Nintendo Entertainment System, it was pretty easy to see where the pixels are. But if we take a slightly more modern graphic, that gets a little bit more complex. You're probably thinking to yourselves, where are the pixels on this screen? Everything's smooth. There are no pixels. But if we zoom in, there we go. We can see all the pixels now. Here they are. So there you have it. Everything on your computer screen is made of pixels. Even your user interface in Windows is made out of pixels. I will show you. Let's zoom in. And there we go. Now we can see what are those little pixels. And is it possible for me to zoom back out? Yes, it is. There we go. Okay, back to the slideshow. So we've established everything is made from pixels on a computer. And by the way, pixels is a combination of two words. It means pixel, element. Both those words combined together. I believe the term is portmanteau or portmanteau or something like that. It's just some French word that just means two words merged together to make a new word. Okay, so in the exam, they could ask you about black and white images. And as we can see in this image, this is clearly a 5x5 image made out of pixels with just two colors. So they could ask you to represent this image in binary. They could also ask you what the resolution of the image is, what the bit depth is, and what the file size is. So if you would like to pause the video and give this a go by yourselves, just have a think about these 4 questions, then go for it. Otherwise, continue watching. Okay, so in terms of the answers for this, represent this in binary. Well, we could make the assumption that 1 is black and 0 is white. And here we have it. So the black pixels are represented as 1s, and the white the white pixels are represented as 0. Do bear in mind they could specify what they want you to do in the question, so they could say 0 is white and 1 is black. Just make sure you read the question properly before answering it. The resolution is just 5x5, so when we mean resolution, we just say what is the width and what is the height. The bit depth is 1. Now that is a phrase that might be brand new to you this lesson. Bit depth just means how many bits are needed to represent each pixel. Well, in this case, we've only got 2 colors, 1s and 0s. Black and white, 1 and 0. So there's just 1 pixel in each. 1 bit in each pixel. Therefore, the bit depth is only 1. The file size is calculated by multiplying the resolution, so 5 times 5, by the bit depth. So there are only 25 bits in this image. Now, a more complex question they could ask you is an image with color. This is where things get a little bit more tricky. Well, we could assume that white is 0 and black is 1. But what about red? We can't have 0.5 in this situation. So I just want you to have a think about how could we represent more than 2 colors? How could we represent red in this example? Just pause this video and have a think about it before continuing. Okay, so the solution is we double the number of bits that's inside each pixel. So instead of representing white as 0, we're now going to represent 0, 0 as white. Red we can represent as 0, 1, and black as 1, 1. Even though we're not using blue, we've still added it in there anyway, because this bit pattern of 1, 0 would have just been wasted otherwise. So we might as well just stick it in for the sake of it. Otherwise we would just have 1, 0 doing nothing. Okay, so in terms of how this would be represented in binary, we're going to have 2 bits per pixel as a result. So here are our black pixels here. Here's an example of a white pixel. And here is an example of our red pixel by here. The bit depth has now increased to 2. So we've got 2 bits per pixel. So the file size is now 50 bits because we're doing the bit depth times by the resolution, which is still 5x5. And if you don't believe me, you can even count up all of these individual bits if you really wanted to. It's important to note that the bit depth is proportional to the number of colours that you're using on your screen. So we've got a bit depth of 2, which means that we can have a maximum of 4 colours on our screen. I just want you to pause this video and have a think about how many different colours can we represent with 3 bits. How many different colours can you represent with 3 bits? Okay, so representing colours with 3 bits. So let's take a 3-bit number in binary. So that's the number 7 in binary. So some students might think, well, you could represent 7 different colours then. Well, that's not the case. You can represent 8 different colours. So we've got colour number 1 and colour number 7. Sorry, colour number 8 down here. So we've got 0 in binary, 1 in binary, followed by 2, followed by 3, followed by 4, 5, 6, and then finally by 7. So we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 different possibilities for colours in our image. And normally they're encoded in such a way that you might have one end of the spectrum up here, another end of the spectrum down here, and all of the colours in between. Alright then, one final thing before we end this video. I'm going to give you a practical application to this imaging stuff that we've just been talking about with bit depth and resolution and things like that. So let's take this image and I'm going to open it up in Paint, and you can try this at home with whatever image you like. So I'm going to do File, Save As, and I'm going to save it as a 256 colour bitmap. And what that means is that there are 256 colours available. What that also means is that there are 8 bits per pixel, because an 8-bit number, there are 256 different combinations available. Okay, we've just lost some colour there. Let's save it again. Let's make it into a 16-bit colour. And by the way, 16-bit colour, that is 4 bits per pixel. We've lost some more colour. And if I save that again and go to monochrome, that's just going to be black and white, 1 bit per pixel. And there we have it. There is our picture. And let's look at the file size difference. 50 kilobytes. Whereas before that, I think our file size was over 1 megabyte. So that's quite a massive difference. It's because there's way less data in the image. In fact, I'm going to make this my background image just for fun.